Good day, students. Welcome to our lesson for this week. Today, we are going to discuss a special technique in integration, trigonometric integrals. Before we start our discussion, let us have a review on the following trigonometric formulas: tangent and cotangent identities, reciprocal identities, sum and difference formulas, Pythagorean identities. So we are going to use these Pythagorean identities in our lesson today. Even and odd formulas, double angle formulas, co-function formulas, sum to product formulas, now let's have the solvable groups of trigonometric integrals. Group 1, number 1, the integral of sine to the mu cosine to the nu du. Number 2, the integral of sine to the mu du. Number 3, the integral of cosine to the nu du, where m and or n are positive integers. Now let's have the group 2 of solvable groups of trigonometric integrals. Number 1, the integral of tangent raised to the m u secant to the n u du. Number 2, the integral of tangent to the mu du. Number 3, the integral of secant to the n u du, where m and or n are positive integers. Lastly, let's have the group 3 of solvable groups of trigonometric integrals. Number 1, the integral of cotangent to the mu cosecant to the n u du. Number 2, the integral of cotangent to the m u du. Number 3, the integral of cosecant to the n u du, where m and or n are positive integers. First, let's have the group 1 of solvable groups of trigonometric integrals. So our given will be based on the structures of each trigonometric integrals from group 1. So remember that m and or n are positive integers. For example, number 1, the integral of sine cube y cosine to the 1/2 y dy. So the first thing to do is for us to have a differential. So since we have sine cube y there, we can separate sine square y and sine y. So now let's go. We're going to have the integral of sine square y cosine 1/2 y sine y dy. So why did we choose sine y to be beside dy? Because 3 is the positive integer. 1/2 is not an integer, okay? So hint, let us use this trigonometric formula. Sine square u equals 1 minus cosine square u. So let us change sine square y to 1 minus cosine square y. So now we have the integral of 1 minus cosine square y times cosine raised to 1 half y sine y dy. And then let us represent u. Let u be equal to cosine y. And get the du. Du is equal to negative sine y dy. So since we only have sine y dy there, so let us express it as negative du equals sine y dy. So our given will be in this structure. The integral of 1 minus u squared times u to the 1 half times negative du. So let us put the negative sign outside the integration symbol. Now we have equals negative the integral of 1 minus u squared times u to the 1 half du. Let us distribute u to the 1 half. Let us multiply u to the 1 half to 1 and negative u squared. That's why we're going to have the minus or negative the integral of u to the 1 half minus u to the 5 over 2 du. So let us distribute the negative sign outside the integration symbol. Multiplying negative 1 to u to the 1 half and negative u raised to 5 over 2 will result to u to the 5 over 2 minus u to the 1 half. So now we have the integral of u raised to 5 over 2 minus u raised to 1 half du. And as you can see, it is already integrable. So let us integrate. Applying the basic principle of integration, we're going to have 2u raised to 7 over 2 over 7 minus 2u raised to 3 over 2 minus 3 plus c. So substitute u, which is cosine y. So now we're going to have equals 2 over 7 cosine y raised to 7 over 2 minus 2/3 cosine y raised to 3 over 2 plus c. So we can accept this as our final answer. Number 2 example, the integral of sine raised to 5 2t dt. So since we only have sine here, so it's very obvious that sine will be our differential. So let us split sine raised to 5 2t into sine raised to 4 2t and sine 2t. So now we're going to have the integral of sine raised to 4 2t times sine 2t dt. So since it is expected for us to use the Pythagorean identities, we aim to have sine squared 2t. We're going to have sine squared 2t if we're going to express sine to the 4 2t as sine square 2t raised to 2. That's why we did this. Now we have the integral of sine square 2t square times sine 2t dt. And then remember this trigonometric formula, sine square u equals 1 minus cosine square u. So we're going to substitute. We're going to change sine square 2t into 1 minus cosine square 2t. Now we're going to have the integral of 1 minus cosine square 2t square times sine 2t dt. So let u be equal to cosine 2t. Get du. Du is equal to negative 2 sine 2t dt. So remember the differentiation of trigonometric functions. So since we only have sine 2t dt there, we will be having negative 1/2 du equals sine 2t dt. Okay? So here, it's like applying the principles of integration by substitution. So change u, change cosine 2t into u. So now we're going to have equals the integral of 1 minus u square times negative 1/2 du. Okay? So just apply the necessary arithmetic here. So we put negative 1/2 outside the integration symbol, and then we expanded 1 minus u square raised to 2, applying the principle of squaring a binomial. Where if we square 1 minus u square, the result will be 1 minus 2u square plus u to the 4th. Then bring down the u. So now we have negative 1/2, the integral of 1 minus 2u square plus u to the 4 times du. So as you can see, 1 minus 2u plus u to the 4 du is integrable. So let us integrate it. We're going to have negative 1/2 times u minus 2/3 u cubed plus 1 over 5 u to the 5th plus c. The basic principle of integration was applied. And then substitute u, or the value of u, which is cosine 2t. So now we're going to have equals negative 1/2 times cosine 2t minus 2/3 cosine cubed 2t plus 1/5 cosine to the 5 2t plus c. So this can be accepted also as our final answer. If you want, you may distribute negative 1/2. Now let's have the solvable groups of trigonometric integrals, group 2. So we have here tangent and secant. For example, number 1, let's have the integral of tangent to the 5th x, secant to the 4th x dx. So let us get one tangent x and one secant x from our given. That's why this will be equals the integral of tangent to the fourth x secant cube x tangent x secant x dx. As you can see, you are familiar with this tangent x secant x dx. You are familiar with secant x tangent x dx. So let us just interchange the position. But before that, since we are expected to use tangent square x from the Pythagorean identities, just like what we have did from our previous given, let us express this as a squared term. So tangent to the fourth x can be expressed as tangent square x raised to 2. Okay, then let's bring down the other factors. So now we have the integral of tangent square x raised to 2 secant cube x tangent x secant x dx. So we are going to use this Pythagorean identity. Tangent square u equals secant square u minus 1. So we are going to change tangent square x into secant square x minus 1. So now we're going to have the integral of secant square x minus 1 raised to 2 secant cube x tangent x secant x dx. And then expanding it, applying squaring of a binomial, the square of secant square x minus 1 is equal to secant to the fourth x minus 2 secant square x plus 1. So now we have the integral of secant to the fourth x minus 2 secant square x plus 1 times secant cube x tangent x secant x dx. Okay, so this is what we got from the previous slide. And then let us distribute secant cube x. Let us multiply secant cube x to all the terms inside the parentheses, since they have secant also aside from 1. But when you multiply secant cube x to 1, it will become secant cube x. So now we have the integral of secant to the 7x minus 2 secant to the 5th x plus secant cube x. And then like what I've said before, this is tangent x secant x dx. We can express this as secant x tangent x dx. Okay, now we have the differential. So let u be equal to secant x. Du is equal to secant x tangent x dx. So remember, the derivative of secant u is secant u tangent u du. Okay, so we just apply the derivative of secant x, or derivative of trigonometric function. Okay, so since we have this, we can change this into u and du, or substitute u and du. So now we have the integral of u to the 7 minus 2u to the 5th plus u cubed du. Okay, so since this is already integrable, let us just integrate this. Applying the basic principle of integration, we're going to have equals u to the 8 over 8 minus 2u to the 6 over 6 plus u to the 4 over 4 plus c. So we have this, and then let us just substitute the value of u, which is secant x. So now we're going to have secant x raised to 8 over 8 minus secant x raised to 6 over 3 plus secant x raised to 4 over 4 plus c, or 1/8 secant to the 8x minus 1/3 secant to the 6x plus 1 over 4 secant to the 4th x plus c. So either of the two can be your final answer. Okay, so look at the way we can write our answer differently. So remember, when we are raising a certain, if we are raising a trigonometric function to a certain power, we can just put the exponent there before the variable. So like this one, the indicator is second for the, yeah, that's it. The argument is second to the 8 and then x. Okay? Now, it's your turn to solve the following practice exercises. Apply what you have learned to answer or to solve the following items. Number 1, the integral of sine to the 1/3 x cosine to the 5th x dx. Number 2, the integral of cosine cube 1/4 x dx. Number 3, the integral of sine square z cosine square z dz. Number 4, the integral of sine to the 4th 1/3 t dt. Number 5, the integral of tangent to the 5th 1/3 t dt. Number 6, cube root of tangent x secant to the 4th x dx. Number 7, the integral of tangent to the 4th y dy. 8, the integral of cosecant cube x cosec or cosine cube x dx. Number 9, the integral of tangent to the 5th x secant to the 4th x dx. Number 10, the integral of cosecant to the 4th x cotangent to the 4th x dx. Number 11, the integral of sine cube x dx all over cosine to the 4th x. 12, the integral of tangent to the 8th x dx. Number 13, the integral of sine to the 7x dx. Number 14, the integral of cosecant square x tangent cube x dx. Number 15, the integral of secant raised to 5 over 2x tangent x dx. Number 16, the integral of sine 2x dx over 1 plus sine square x.